So good morning, my name is Susanna Bardini, and today I'm going to present you OptoSens, a prototype of mask for sleep quality monitoring. So first of all, just a brief introduction. I'm graduating in biomedical engineering, and my research area focuses on wearable devices for personal well-being monitoring, and I'm willing to start a PhD within this area. So we can say that nowadays we are quite used to collect several physiological parameters in order to increase our personal awareness for what concerns our habits related to physical activity, nutrition, stress management, and sleep quality. And in particular, today we will focus our attention on this last one, so on sleep monitoring, as it is of fundamental importance in our everyday life, as it is crucial for several cognitive and metabolic functions. Traditionally, sleep monitoring is tracked by identifying the sleep stages that characterize our rest, and in particular, light sleep, REM, and deep sleep stages, that together with the awake phase are usually represented in a graph like this, in which we can appreciate the time percentages that we spent in each sleep phase. But let's now go deeper into the techniques that allows us to identify the sleep stages. We have several tests that allows us to identify and to monitor the clinical sleep disorders that might affect. And even if we will not focus today on this area, we can mention polysomnography and actigraphy as the two tests that today represents the state of the art. We have then also several devices that allows us an autonomous at-home monitoring and that provides us with more immediate feedbacks. We have devices that do not even require the direct contact with our body, but they are meant to be placed near our bed or under our mattress in order to track our snoring or our body movements during rest. And then we have also wearable devices that aims to continuously collect biosignals related to brain or muscular activity, heart rate, or eye movements. And examples of such devices are, for example, headbands or smartwatches, rings, or even sleep masks. And in particular, sleep masks are gaining an increasing attention in recent years' research, as they are particularly interesting as on one end allows to limit the possible external noise sources that might affect our physiological sleep. So it's, for example, the ambient light. And on the other hand, allows to embed systems that are less invasive and that aims to monitor heart rate or eye movements. And in particular, eye movements is a technique that is gaining an increasing attention because it seems to be particularly feasible for this kind of monitoring. And traditionally is exploited with electrooculography, that however, it is not exploitable in our everyday life as it is quite invasive and requires previous medical knowledge. And so in order to correctly place several electrodes, and so it is not feasible for a daily monitoring. And for these reasons, there are studies that aims to find more feasible solution for a daily monitoring based on optical systems or on magnetic sensors. And it is within this context that I had the idea to implement a prototype of mask based on an optical system that is less invasive, less bulky, do not require any previous medical knowledge to the user, and it does not affect our physiological sleep. So here we have a picture of OptoSens. As I just mentioned, the prototype is based on an optical system that is composed by an infrared LED and 3 photodiodes put around it. The working principle is basically based on the emission of an infrared light that is reflected on our eyelid and detected by 3 photodiodes. And to date, the device works on the Arduino Nano RP2040 Connect. So OptoSens has two working modalities. The first modality is the calibration one that allows the user to verify at the first usage of the mask that the device is correctly placed on our face, and in particular that the optical system is centered with the center of our eye in order to allow a proper monitoring. So the user can verify this by checking for the match between the real direction of displacement of the eye under the eyelid and the output printed on the screen. And such function has been implemented by associating to the evolution of the signal over time the possible direction of displacement of our eye under the eyelid. The second modality is the actually monitoring modality that continuously record the mean value detected by the 3 photodiodes that actually corresponds to the real mean displacement of our eye. And in order to associate to such signal the different sleep phases, I've developed a post-processing algorithm that was initially based and parameterized starting from the classification performed by the Samsung Galaxy Watch 5 that I initially exploited as ground truth. But let's now go to analyze the structure of the algorithm. It is organized on two parts. The first part allows to identify the deep sleep, REM, and light sleep phases, while the second part allows to discriminate the awake stage. So starting from the signals collected across different recordings and among two different users, I have identified patterns that were characteristic of the different sleep phases. And in order to properly classify such phases, I first of all normalized the signal. I reduced the noise of such signal, and finally, I set experimentally two thresholds that I've compared with the variance of the signal obtained so far in order to discriminate the light sleep, REM, and deep sleep stages. At this point, however, the algorithm wasn't able to discriminate the awake stage from the light sleep phase, as we can observe the two patterns differs only for the frequency of the signal. And so at this point, the algorithm starting from the samples belonging to the intervals already classified as light sleep stages, computes the Fourier transform in order to be able to associate the intervals characterized by a peak at higher frequencies to the awake stage and the intervals of the signal characterized by a peak at the lower frequencies to the light sleep phase, in order to be able finally to correctly classify the four stages that characterize our rest. So here we can see a summary of the steps that compose the algorithm that I've just described, organized on the two parts. Then at this point, I found interesting to compare the classification proposed starting from the optical system on which actually the working principle of OptoSens is based on, with another classification carried out also within the same device, but starting from the gyroscope data, in order to be able to prove the internal consistency and coherency of the device. For this classification, actually I focused my attention on the identification of the light sleep phase, because to date, the second technique is quite noisy, and so I had to take into consideration the breathing rate and the body movements that in the light sleep phase are more constant in time and limited, and so it was a feasible phase in order to perform such comparison. So here we have an example of light sleep classification starting from the data recorded by the optical system, and an example of light sleep classification starting from the elaborated gyroscope data. We can see that the two classifications are coherent, and in particular, in order to identify the light sleep phase starting from the second classification technique, I have associated the light sleep phase to the portion of the signal that overcomes a threshold that I have experimentally set respect to the rest of the recording where the signal remains under such threshold. So summarizing what I've described so far, I started from the classification performed by a commercial device. Then I developed my own algorithm based on, in order to classify the sleep phases starting from the data collected with the optical system. And finally, I proved the internal consistency and coherency of the device by comparing such classification with a classification performed starting from the gyroscope data, focusing on the identification of the light sleep phase. And for what regards the light sleep time computed, starting from the gyroscope data, we can say that this last classification somehow overestimates sometimes the time spent in the light sleep phase respect to the classification performed starting from the optical system and the ground truth data. But however, it was interesting to have such comparison of two techniques exploited within the same device. To date, OptoSens provides a feedback to the user, so we can observe that we have a qualitative feedback from which we can observe the time percentages that we spend in each sleep phase. And then we have also the possibility to download a file reporting such data. And also we have a comparison with the typical time intervals reported in the state of the art. So why OptoSens? we can say that OptoSens is a device that is less bulky, less invasive. It is easier to use because it does not even require previous medical knowledge to the user, and it does not affect with our physiological sleep. And for what regards possible future works, I'm actually working on the substitution of the Arduino Nano with the Nicla Sense Me that is characterized by a smaller form factor and a wider range of industrial grade sensors. And moreover, I'm working on the implementation of real-time classification in order to be able not only to provide a feedback to the user, but also to interact with the user itself. And finally, I believe that it might be interesting also to add the possibility to modify the orientation of the infrared LED and the free photodiodes in order to overcome the rigidity typical of the mask structure. So finally, starting from this work, I believe that it might be interesting to expand this project in order to be able to evaluate how the environment affects our sleep quality, and also to be able to evaluate if the sleep phases that occurs during our rest somehow affects the feeling that the user has of his rest. And this on one end. On the other hand, I believe that it might be interesting to evaluate also the interaction between sleep and our cognitive performances and stress management, and also the relationship between our sleep and our physical activity and nutrition habits. So thank you for your kind attention, and I will be more than happy to answer to your questions.
Thank you, Susanna. So you have used like real-time classification. So which are the advantages of use such type of classification?
So yes, thank you for your question. I believe that exploiting a real-time classification could open several advantages and several new possibilities. For example, it might be interesting to be able to connect OptoSens to an alarm clock in order to interact with the user itself in real time. So for example, at the awakening time, if the user is in the REM phase, the alarm clock could be postponed in a predefined time range of, let's say, 10 minutes in order to allow the user to wake up in a more appropriate sleep phase, for example, in the light sleep phase, in order to provide the user with a better feeling of his quality of sleep.
Okay, thanks. And up to date, the classification is based on the data collected with the gyroscope as being exploited for the validation of the classification of your optical system. So do you think that it could also be exploited to bring added value to your solution?
Yes, so yes, to date it has been exploited only to validate the system. I believe that by exploiting the NICLA, it might be interesting to introduce a standalone classification based on the gyroscope, or maybe in combination with an accelerometer or other motion sensing sensors, in order to be able to provide a sleep classification based on two different techniques within the same device.